Good day, everyone. And once again, we are back together. And thank you so much for joining us. And as we are preparing towards prelims and our final exams, we obviously will be throwing in one or two questions now and then just to make sure that we revise properly. So if you haven't subscribed, please just make sure you're part of this journey. And, we are working towards 100,000 mark. And hopefully you will be there as part of those who will be adding to our numbers. All right, so I thought today we'll just look at a question on chemical equilibrium. All right, so just to remind ourselves of what we should do, particularly on those calculations that have to do with Kc. All right, now let's get right into the question. It says hydrogen and iodine are sealed in a 2 cubic decimeter container, and the reaction is allowed to reach equilibrium at 700 Kelvin, according to the balanced equation. Okay, so now they say give a reason why changes in pressure will have no effect on the equilibrium position. Now remember, whenever we talk about pressure in this case, remember that what you simply do is to look at the number of moles of gases on either the left or the right hand side, in fact on both sides. Now if you look at this, you'll see that there's 1 mole of gas here, there's another 1 mole of gas, so it means that you've got 2 moles of gas in this case on the left hand side, and you've got another 2 moles on the right hand side, right? So why would pressure not have an effect? Remember, according to Le Chatelier's principle, whenever we increase the pressure, will always favor the side that has lesser moles of gas. So which side has lesser moles of gas here? None of the sides, right? So as a result, an increase in pressure will have no effect, because in this case there are equal volumes of gases on either side. All right, now at equilibrium they now tell us that we've got 0.028 of hydrogen and 0.017 of iodine that are present in the container, and they want us to calculate the initial moles of iodine in grams that was sealed in the container if Kc for the reaction is 55.3 at 700 Kelvin. All right, so now what we'll do is we will just try to draw our table. Okay, so we know that we'll always have in our table, let's start with the initial moles, so that will be initial, that's in moles. Okay, that would be change in moles, and that would be equilibrium moles. Okay, so that would be equilibrium, that's in moles as well. Okay, in fact I just left one column, or rather row in this case, that's for equilibrium concentration. So equilibrium concentration, that would be in moles per cubic decimeters. Okay, so now what they've done here is that they've given us the amounts at equilibrium, and they didn't give us the equilibrium, or rather the initial amounts, right? So they told us that we took a certain amount of hydrogen and another amount of iodine in this case. So that would mean that we didn't know what our initial moles were, right? But we do have equilibrium moles. Now note that they did not say anything about hydrogen iodide at equilibrium. So what does that simply mean? It simply means that we would have started with nothing. So if you want to, we could say, well, the amount of hydrogen we started with, let's call it an X amount, and say the amount of iodine that we started with is a Y amount. We don't know what that amount was, but we do know that we started with nothing in terms of hydrogen iodide, right? And then we skip over to equilibrium. We know that the amount of hydrogen was 0.028. So I'm going to put that amount there. So that would be 0.028. Okay, and the amount of iodine at equilibrium was 0.017. So that would be 0.017. And in this case, we don't have any other information, right? Now, what I would like for us to do is we could actually work out the amount of hydrogen iodide at equilibrium. But first, what we'd need to do is find the concentration of both hydrogen and iodine. So what we're going to do, remember that concentration is number of moles over volume. Our volume, remember, it's given as 2 cubic decimeters. So what we're going to do is say, okay, we've got 0.028. Okay, that's divided by 2. Okay, so that would give us 0.014. Okay, and in this case, we've got also for iodine, we've got 0.017. Okay, and now we divide that by 2, so that would give us 0.0065, actually 75, right? So 7, that's 14. Okay, so that would give us let me just actually work it out. 0.017. My mind just froze there for a moment. 0.017. Okay, I put in so many zeros. 0.17, and we divide that by 2, 0.085. For a moment, my mind just froze there. Okay, so now we can work out the amount of iodine, or hydrogen iodide rather, at equilibrium. But remember, we're given the Kc value, right? We know that's going to be the molar concentration of hydrogen iodide squared. Remember, the coefficient is 2, right? Divided by the molar concentration of hydrogen, okay, as well as that of iodine in this case, right? But we know that equilibrium is 55.3? Yes, it is. Okay, so that's 55.3. Now we can actually substitute those values that we got, right? We want hydrogen iodide. Okay. But what do we have? We've got hydrogen, which is 0.014. We've got iodine, which is 0.0085, okay, which is equal to 55.3. Obviously, if we put it as a fraction, that's over 1. So all we're going to do is just cross multiply. Hi squared would simply be Hi squared times 1, okay? Now we're multiplying that whole thing there. So that's 0.085 multiplied by 0.014 multiplied by 55.3, and that gives us 0.0606807. So we're just going to take the square root. So we take the square root of our answer, and that gives us 0.08. So in this case, it means that the concentration of hydrogen iodide will be 0.08. If you want to, you can say 0.81 at equilibrium. That's the concentration. So that would be 0.081, okay, at equilibrium. Mind you, this is concentration, so this should be moles per cubic decimeters. Okay, right. But now we can actually find out the number of moles for that. So how do we do that? Remember, so that's going to be concentration is number of moles over volume. Our concentration is 0.081. Our number of moles is what we want, and our volume is 2. So we just multiply that by 2 in this case, and we get 0.162. So I've got 0.16. If you want to, let's say 0.162. Now, ladies and gents, this is where I want you to remember, right? We use our ratio when it comes to only the change in moles, right? So look at this. We started with nothing, and at the end we've got 0.162. How much did we form? We formed 0.162, right? So now we want to find out what would be, in terms of ratio, what would be the amount of iodine in this case. Now we go to our formula and say, well, for every 1 mole of iodine, we get 2 of hydrogen iodide. So for how much will I have 0.12? So in this case, for every 1 mole of iodine, I get 2 moles of hydrogen iodide. So for how much will I have 0.162 of hydrogen iodide? And all we do is cross multiply. 2 times x will be 2x, and 1 times 0.162 is 0.162. And I can divide that by 2 in this case, and that will give us 0.81, right? So in this case, I will just simply say that amount. It means that this is the amount of hydrogen and as well as iodine, so 0.81, but that would be the same for 0.81 for hydrogen. Now, I want you to note, we can actually get the amount in this case exactly as it is, because remember, you started with Y amount, you used 0.81. How much do you have at the end? That's 0.017, right? So you can actually remember what they wanted for us is the initial amount of iodine, right? So in this case, and by the way, they wanted that in grams. Okay, so what we can find is the number of moles. We know we started with Y, right? And we used an amount of 0.81. And at the end, we were left with 0.017. Okay, so that would be 0.017. So it means that our initial amount of iodine in moles, okay, would be actually the addition of that. So that would be 0.827. But of course, if you want to round this off, it means that the number of moles of iodine would be equal to 0.83 moles. This would be the initial moles. Okay, but now remember, we want to find out in this case, what would be the equilibrium, or rather the initial amount, but not in moles this time around, but we want the mass. Okay, so obviously we would need the periodic table. Oh, I actually didn't prepare it for this. Okay, so what we would do is we would go into the periodic table. We use number of moles, which is equal to mass divided by the molar mass. Okay, right. So we divide that by the molar mass, and at the end of the day, we simply take that 0.83 moles. We want the mass. And remember, iodine, in this case, we would go to the periodic table. I'm actually trying to find it here. All right, so that I don't waste any more time. I'm actually looking for the periodic table frantically. Right. If I don't... Okay, there we go. So I'm just going to use my periodic table here. So iodine is 127. Okay, so remember, you've got 2, it's I2, right? So you're going to say 127 multiplied by 2. So the mass in this case would be 0.83 times 127 times 2. Okay, so I'm going to say, okay, that's 0.83 times 127 times 2, and that would give me 210.82 grams. All right, so that would be the amount, or rather the mass of iodine at that would be the initial mass of iodine. Right, so quickly to go into the next part. All right, they say, what do the parallel lines... Oh, actually, they gave us a graph there. They say the reaction between... so the reaction versus time graph represents, rather, different changes made to the equilibrium mixture. Now, I want you to note that equilibrium mixture actually started at equilibrium. How do I know that? Because the rate of the forward reaction is actually equal to the rate of the reverse reaction at that point. So now, what I want you to note there is that when you started with equilibrium, I just need to have a bit of fresh air here. I'm actually recording from the car. So I hope you don't mind if you keep hearing windows open and people passing. All right. So what we're going to do is we note there's a difference there, or rather there is a change that takes place at minute number 2. Okay. Now they ask us, what do the parallel lines in the first 2 minutes indicate? They actually indicate that our system is at equilibrium. How do I know that? Because the rate of the forward reaction is equal to the rate of the reverse reaction. So when you look at that, both of them are actually equal in the first 2 minutes. Okay, right. Now, they say state 2 possible changes that could be made to the reaction conditions at t is equal to 2 minutes. Okay, so at 2 minutes, what happened in that case is that we could have either added a catalyst. Why? Because remember, what a catalyst would do is that it would increase both the rate of the forward as well as the reverse reaction equally, right? So we could have added a catalyst in that case, right? But also think about it, because our volumes are the same, right? When we increase the pressure in this case, as much as it's not going to favor any of the 2 reactions, but it will increase the rate of both the forward and the reverse reaction equally. So what could we have done at t is equals to 2 minutes? We could have either added a catalyst, or in this case added or increased the pressure of the container. All right. Now, the next question. They say to us the temperature of the equilibrium mixture was changed at t is equals to 4. Now, I want you to note in this case, we decreased, or rather, let me just, whatever they did to temperature decreased the rate of the reaction. But I want you to note that it's the forward reaction that was decreased the most, okay? That was the most severely impacted, okay? So I want you to please remember this, that whenever you change temperature, the reaction that responds the most because of the change is the one that depends on temperature the most, okay? So if you think about it, so it means it tells us that the forward reaction depends on temperature. So it tells you that the forward reaction is actually endothermic, okay? So they're asking us the question, is the forward reaction exothermic or endothermic, okay? Right. So we're going to, let's explain now. So we did say it's endothermic, right? Okay. So they say fully explain the answer. So we know it's going to be endothermic. And when we fully explain in this case, we're going to simply state a decrease in temperature, okay? So a decrease in temperature will always favor rather the exothermic reaction, all right? So if you note there, all right, a decrease in temperature favors the endothermic, rather the forward reaction in this case. So the decrease in temperature in this case, rather, let me put it this way, a decrease in temperature affected the reaction that depends on temperature the most, okay? So it means that the forward reaction was affected, okay, meaning that the forward reaction is endothermic, and as a result, that is our answer, okay? I hope that made sense. Right. And then the final question, they say, how will the change influence the Kc value, okay? So I want you to note in this case, it's only temperature that affects, or rather that changes the Kc value. So definitely there will be a change in this case, right? So how will this change affect the Kc value? All right. I want you to note in this case, because we decrease temperature, okay, it means that the forward reaction was severely impacted in this case. So that will decrease the amount of products that are formed, and so Kc would decrease in that case. Okay, right. So it means you'll form less products, and so Kc will decrease. All right, and then finally, they say what change was made to the equilibrium mixture at T is equals to 8. So what happened at T is equals to 8? So we know it's not temperature, okay? We know it's not, it's not addition of a catalyst, or in this case pressure. So it must have been, the concentration. So I want you to note in this case, there was a steep decrease in the reaction rate of the forward reaction, okay? But immediately what happened, okay? So it means our forward reaction started picking up, right? So what would have happened? It means we must have decreased the concentration of one of our reactants, okay? So a decrease in the concentration either of hydrogen or iodine, but it was a decrease in concentration of our reactants. How do we know that? Because it severely impacted, in this case, the rate of the forward reaction. Okay, right. I hope that made sense, ladies and gents. I'm going to leave this here, and please remember to subscribe, and please tell as many people as you possibly can about our channel, and we will be continuing to make sure that we give you good quality content as we prepare towards the prelims. Otherwise, your favorite uncle will see you again next time. Sharp, sharp.